All right, well, AP Stats, this is our second to last section of notes for the year. So, how exciting is that? So, to kick things off, if you have not already, I posted a video after the notes video from the most recent section that was called Mentos and Soda. If you've not done this and you've never seen this before, I'd highly recommend watching that video. Kind of does a good job of letting you visualize what we're talking about today. But when Mentos are dropped into a newly opened bottle of Diet Coke, or any soda actually for that matter, carbon dioxide is released from the Diet Coke very rapidly. It causes the Diet Coke to be expelled from the bottle. Will more Diet Coke be expelled when there is a larger number of Mentos dropped in the bottle? So two statistics students, Brittany and Allie, decided to find out. They used 16-ounce or 2-cup bottles of Diet Coke. They dropped either 2, 3, 4, or 5 Mentos into a randomly selected bottle, waiting for the fizzing to die down, and measured the number of cups remaining in the bottle. Then they subtracted this measurement from the original amount in the bottle to calculate the amount of Diet Coke that had been expelled in cups. We've been given output from a regression analysis shown below. So as you can see on the left, we've got our scatter plot, including a line of best fit, and then we also have a residual plot. So that's kind of a nice thing to have as well. Now, instead of giving us the actual data from the experiment, they gave us this computer output, and that's kind of the idea of today's notes. We're really not going to do a whole lot of new stuff. It's just going to be presented to us in a slightly different way. So first off, using that computer output, what is the equation of the least squares regression line? And then we need to define any variables that we use. So obviously you can see based on this computer output, it's giving us a whole lot of information. What you need to look for when you're writing your equation is this coefficients column. Not the SE coefficients or the standard error coefficients, but just the regular old coefficients. Now notice that one of them is what's called a constant. In other words, that will be your y-intercept. The other for Mentos is what we're going to use as our slope, since we're going to be changing our graph and our data based on the number of Mentos that were dropped ideally. So when we write our equation, I'm going to go ahead and do it using the variables that were given. So the amount of soda that was expelled, hat. And if you wanted to say y hat, you would just have to later on define that y hat was equal to the soda expelled, is equal to your y-intercept, so 1.00208, plus your slope, which was 0.07083, multiplied by your number of Mentos. So if you're choosing to write this as an equation with y and x, that's okay. Just make sure you define those later on. If you use the actual terms and context in your equation, you don't have to do that, which is kind of nice. So for B, interpret the slope of the least squares regression line. Okay, so our slope, which was right here, was 0.07083. Let's say that for each additional Mento that we use, we would expect for an additional 0.07083 cups, and be careful because they were talking about this in cups, of soda to be expelled. Okay. So next question for part C, what is the correlation? So correlation, remember, is your R value, and it actually doesn't give you R. It does, however, tell you what R squared is. So it tells us that R squared, and make sure you convert this to a decimal, is 0.062. So if we want R, we just need to take the square root of that. So take the square root of 0.602, and that should tell us what our correlation is. So I'm going to type that in real quick here. We'll see what that is. And on my end, I'm coming up with 0.776 to 3 decimal places. So I mean, as far as a strength, I would say it's probably got a moderate correlation. Definitely a positive correlation since it's greater than 0. Okay. So for part D, is a linear model appropriate for the data? Well, let's go check our residual plot. So remember, the residual plot is what you use to check to see whether a linear model seems appropriate. And I mean, yeah, looking at your residual plot, I would say that there is no apparent pattern. They are about as equally spread out as they could possibly be. So I would say a linear model is definitely appropriate. And so for the explanation, we would just have to say something along the lines of that the residual plot does not have any patterns, and that's all we've got to say. Rewrite some of this, going too quick in places. Any patterns, cool. So then, would you be willing to use the linear model to predict the amount of Diet Coke expelled when 10 Mentos are used? Well, that's a lot of Mentos. So let's see. In our experiment, we only had anywhere from 2 up to 5 Mentos. So the answer to this is definitely no. And I'll give you a second to think about what is that magical word that I would maybe be looking for here, that AP would maybe be looking for here. This is an example of if you said extrapolation, you're right. All right. Next up, and again, you're probably noticing that really with the exception of that very first part with computer output, the rest of this is all reviewed. Actually, it's a good problem. It'd be a good problem that you could potentially see on the AP exam. So just kind of keep that in mind as we're working through this. This would be what would look very similar to an AP free response type question. All right, so for F, continuing through this, calculate and interpret the residual for a bottle of Diet Coke that had 2 Mentos and lost 1.25 cups. So at least 2 Mentos, that's going to be what we put into our equation. So let's see what that would be. That would be taking 1.00208 plus 0.07083 multiplied by the number of Mentos, which is 2. This will be our prediction. So this will be our soda that's being expelled hat, which I'll just for shorthand say that that's going to be the same as y hat at this point. And let's see what that comes up with. So 1.00208 0.07083 multiplied by 2 is a predicted value of 1.14374. So now to find our residual, we're going to take our observed minus our expected. So in doing so, our observed is 1.25 minus our expected of 1.14374 gives us a difference of 0.10626. And then remember, since that is a positive value, we're going to say that we underestimated the amount of soda that was expelled by 0.10626 cups. Okay, cool. Just a couple more things for this one and we'll be done for the day. So interpret the values of r squared and s. Well, r squared, just as a reminder, was 60.2%. S we hadn't used yet, but it did actually give us our s value as well, is approximately 0.07. I'll just go to the nearest hundredths place there. So 0.07. Okay, so let's interpret r first. And this is where, going back to what we talked about in the previous video, we're going to kind of just fill it into that form sentence that I gave to you. So we're going to say that approximately, fill in the blank, so approximately 60.2% of the variance in the response variable. And to put that into context, variance in the amount of Diet Coke expelled is accounted for by the least squares regression line. Do some abbreviating there to get this done a little quicker. Cool. So now let's go back and do S. So S being 0.07, we would say on average, the residuals were about 0.07 cups away from our regression line. Okay. Awesome. I think we've only got, we got about one more thing with this part, and then we've got one more example to look at for this section. Like I said, this is a little bit longer one, but the other two kind of make up for it being a little bit short. So if the amount expelled were measured in ounces instead of cups, how would the values of R squared and S be affected? So really what we're doing, all we're doing is changing how it's measured, we're changing the label. And remember that R squared does not have a label, so R squared would be unaffected. Even though that you're changing how it's measured, the relationship between the two would stay the same. S would be different because of that label. You would have to convert cups into ounces, and that would be really the only difference there. Okay, so last thing for this section, how can you calculate the equation of the least squares regression line using summary statistics? And is this on the formula sheet? Well, the answer to the second part is yes. All of this is on your formula sheet. In fact, it's the very first page. You essentially need 5 things in order to calculate a least squares regression line. You need x bar, you need y bar, you need s of x, you need s of y, and you need r. And the reason for that, here are the equations that we're going to use. The first equation is the one for least squares regression line. So that is y hat is equal to b null plus b sub 1 r, or multiplied by x, excuse me. Second equation that we'll need is the equation that will help you find the y-intercept, or b null, which is that you're going to take y bar minus b sub 1 multiplied with x bar, which in order to use that equation, we need to then find b1. So really we're going to end up using these equations in reverse. In order to find b1, you take r multiplied by s sub y divided by s sub x. Okay, so just to show you how this works, I've got an example here for us. We've got data that came from a random sample of 15 high school students, investigated the relationship between foot length and height. The mean and standard deviation of the foot lengths were 24.676 centimeters with a standard deviation of 2.71 centimeters. The mean and standard deviation for the heights was that y hat was equal to 171.43 centimeters, and s of y was equal to 10.69 centimeters. The correlation between foot length and height was found to be r 0.697. Find the equation of your least squares regression line predicting height from foot length, and then show your work. Okay, so again, we're going to kind of use these equations in reverse. So we're first going to find b1. We're going to find that by taking r, which is 0.697, multiplied by s of y, which was 10.69, divided by s of x, which was 2.71. So when we do that, type that into a calculator real quick here. 0.697, 10.69, divide 2.71 is going to be 2.749. Then, now that we've got that, we can find b null. So you notice that we're using those equations that we wrote just in reverse order. So to find b null, you're going to take y bar, which was 171.43, minus b1, and make sure to use the full decimal, so leave that in your calculator, multiplied by x bar, which is 24.76. So we'll type that in now, 171.43 minus our answer multiplied by 24.76, which should tell you that your null is 103.35. At that point, actually, you've got enough for your equation. You'd say y hat is equal to 103.35 plus 2.749 multiplied by x. Now, the only other thing we need to do, it didn't ask us to do anything else besides find the least squares regression line, but since I'm using variables, I do need to define those variables. So remember that y hat is the predicted height based on this least squares regression line, and x represents the foot length. So make sure that since I am using those variables, that they get defined. All right, well, that is our second to last section of notes. The only thing we have left is to just kind of wrap it all together, make sure it all makes sense in that last section. And that's all I've got for you. Have a good rest of your day.